Before we can understand the Casimir effect, we must first discuss virtual particles. Imagine a vacuum, empty space, with no particles. However, this vacuum can be thought of as having particles with zero energy. The Heisenberg uncertainty principle states that there is an uncertainty in energy and time. We cannot be certain that a particle has no energy. This means that in our vacuum of zero energy particles, we actually have virtual particles, which pop in and out of existence. These virtual particles exist in pairs of a particle and its antiparticle, which will eventually annihilate. The more energy the virtual particles possess, the less time they will exist for. The Casimir effect involves setting up an experiment where two thin metal plates are placed 1 micron apart, with a vacuum between the two plates and outside the two plates. As we saw before though, this vacuum is filled with virtual particles. However, the type of virtual particles between the two plates is limited. The wavelengths of these virtual particles between the two plates must be less than or equal to 1 micron. This means that there are more virtual particles outside the plates than between them, which results in a pressure acting on the plates. The equation pressure equals force over area shows us that there is a force acting on the two plates, even though they are within a vacuum. The two plates are pushed together, and we call this the Casimir effect. Finally, we also have the dynamical Casimir effect, first observed in 2011, when one of the plates was accelerated to approximately 5% of the speed of light. By accelerating one of the plates very fast, against the force of the virtual particles, you are doing work on that plate and wrenching the particle and its antiparticle apart, meaning that they can no longer meet and annihilate one another. Since the two particles are not annihilated, they become real particles. However, we need to follow the law of conservation of energy. The virtual particles are given energy from the work done on the plates when they are accelerated against the force of the virtual particles. This means that the virtual particles become real. The dynamical Casimir effect also occurs at the event horizon of a black hole. Virtual particles are created in the vacuum of space, and one of these particles in the pair gets sucked into the black hole, which leaves the other to become a real particle. But in order to obey the law of conservation of energy, we use the equivalence principle from general relativity, which states that in space-time, gravity cannot be distinguished from acceleration. Therefore, the gravity accelerates the particle which has been sucked in by the black hole, which does work on that particle and gives its partner particle the energy to become real. The only place this energy can come from is from the mass of the black hole, which means that over time, the black hole loses energy to produce particles, and we call these Hawking radiation, which is eventually how black holes die.